So, good morning, students. We'll end our topic number four with topic number 9, which is quality assurance, quality control, user manual checklist, and role of inspection in quality control. So, the first one is quality assurance (QA) in construction. Quality assurance are certain schemes that is implemented in construction in order to maintain the standard or the quality of the work in a consistent manner. Quality assurance forms the integral management system in a construction company. The companies generally will have a quality assurance chart that will specify various checks at different levels. In general, a quality assurance plan will involve the following points. First one, training programs for workers and employees. Second one, efficient safety program. Third one, effective procurement system to obtain quality resources and suppliers. Fourth one, reward scheme for innovative works. And the fifth one is a competitive career progress scheme. In continuation, quality control in construction involves periodic inspection of the construction activities and facilities in order to meet the desired standardization as per the contract. Quality control is undergone by a team of QC, that is quality control engineers or special trained teams. For example, the quality control for compaction work conducted for highway project is performed by measuring the soil density. Slump test helps in determining the workability of the concrete. Quality assurance forms a scheme of for good management of construction activities, while quality control undergoes inspection or sampling processes. Quality assurance forms a scheme for good management of construction activities, while quality control undergoes inspection or sampling processes. Quality control focuses on the following. Number one, setting and practicing specific standard for construction. Number two, determining the deviations from the standards. Number three, bringing and taking corrective measures to reduce variation. Number four, standard improvement with time. So the four pillars of construction project quality are meeting the technical specification, delivering on time, cost within the budget, and work without any argument or dispute. So these factors reflect the good quality of the work done in a construction project. User manuals and checklists for quality control. So there are 5 elements of quality control checklist that are vital in making them effective. Some are more obvious to importers while others are often unknown or neglected. The 5 elements include product requirements, packaging requirements, on-site tests and checks, defect classification, collaboration between the importer, supplier, and quality control staff. Next, role of inspection. Inspection is one of the most important parts of quality control. Inspection involves measuring, examining, and testing products, process, and services against specified requirements to determine conformity. An inspection determines if the material or item is in proper quantity and condition. If the inspection is done properly, it helps to a great extent in ensuring proper control on quality of the materials and products. A few common roles or responsibilities are: number 1, carry out quality assessment measures of all the products that are ready to be shipped and incoming raw materials. Number 2, take a thorough look at the plan specifications and blueprints to understand the product requirements. Number 3, reject all the incoming raw materials failed to meet quality expectations and report the issue to the concerned department at the earliest. Number 4, resolving quality related issues, adhering to deadlines. Number 5, providing training to the quality assurance team. Number 6, designing an efficient design protocol which can be used across all domains. Number 7, preparing documentation of the inspection process, which includes detailed reports and performance records. Number 8, recommend improvement measures to the production process to ensure quality control standards are met. Number 9, guide the production team about the quality control issues to enhance the quality of the product. Number 10, monitor customer satisfaction levels. Number 11, monitor the production phase at various levels. So quality management is dependent on quality assurance, and both quality management and quality assurance is as a whole dependent on quality control. So together we can say that quality assurance and quality management comprises of quality control, which is QC. So you can give your attendance now in the chat box. Thank you.
cost and they could have an internal cost. So what we have given here is the quality cost is equal to the cost of quality control plus the failure costs, and the quality control cost is prevention cost and appraisal cost, and the failure cost itself is internal failure and external failure costs. Now if we look at it diagrammatically, if we have this as our quality level and we look at the cost on this side, we have something called the failure cost. The failure cost will keep decreasing as the quality level increases. And finally, we'll have a situation where we have zero defects. Whereas the prevention and appraisal cost will keep increasing as we move towards this goal of zero defects. Now it is up to us to decide what is the level of quality that we will keep. What is the level of quality that is acceptable to us? Because there is a cost involved. Now, in the discussion so far, we've already talked about construction safety. Do you see some parallels between construction safety and construction quality? At least I see several things which are quite in common. When we talked of safety, we talked of prevention of accidents and we talked of the cost of safety. Direct cost, indirect cost, accident having a direct cost and an indirect cost. Then also, there was the whole department of safety. There also we talked about a safety engineer, we talked about a safety audit team, and so on. Those people were also involved in ensuring that the project site is a safe place to work. That is, there are few accidents. In fact, the target is zero accidents. Now, in order to ensure that, there is a cost that is involved, and much like in the case of quality control, there will be quality inspectors, there will be quality audits, there will be quality reports, there will be a feedback mechanism, there have to be records. Both quality and safety inspectors are not mainline execution people. They can be looked upon as people who hinder the progress. So quality control inspector can well say that, well, product being made or the construction activity that being carried out does not meet quality standards, does not meet acceptable standards, and therefore must be stopped. Much as the safety inspector can say that safe practices are not being followed at site, and therefore work must stop. But what has to be understood by the top management or the management of the site is that both of them are an integral part of ensuring a good product at the end of the day. They are part of a team that ensures the reputation of the company and the fact that finally the project or the constructed facility meets standards. So that's how we can kind of see the relationship between quality and safety. That, of course, is an aside. Now let us come to specific situations for a construction project. In this module, we'll not be talking so much about total quality control or total quality management, zero defects, and so on from a theoretical perspective. But the effort will be to identify certain small topics taken from the field of construction, taken from the site, and discussing them from the point of view of safety. So what we are trying to look at from a construction project perspective is quality of materials, components, and systems. That's one way to look at it. The other way of looking at it is to talk of quality of a product versus quality of a process. Now, as far as the first view is concerned, where we are talking about materials, component, and systems, what are the materials that we use at site? It could be cement, steel, concrete, pre-stressing tendons, and the list goes on and on and on. So each of these materials must conform to certain quality standards. And that is what we are talking about when we say that we are talking about quality control of materials that are contributing to a construction project. Moving on, there are components of a structure. It could be beams, slabs, columns, walls. All of them as components, they are made of materials, but there is also a lot of other things that goes into making them. The formwork, the compaction of concrete, the welding if it is involved, and so on. Then there is the system. Finally, it is the system that is the target. The bridge, a building, a factory, a road, a sewer line, and so on. The system is the final product. Moving this way, if we go, in order to ensure that the system performs acceptably, it's important that the components perform satisfactorily, and it's important that the materials perform satisfactorily. So there have to be benchmarks for materials, components, and systems. And that is what is ensured when we talk of quality control and quality assurance in construction projects. Now, coming to products versus processes as far as construction industry is concerned, products could be sleepers, pipes, girders, and so on, which are largely factory-made products. So in this day and age, we are talking about prefabricated members. Now, no matter how much prefabrication we do, we will be able to make certain products, but finally they'll have to be integrated at site to develop a system. We've often seen construction being done with precast girders. Now, those precast girders are factory-made products, but they have to be assembled, they have to be erected at site, and there's a lot of workmanship that goes on while they're at site in order to ensure that the bridge made with them meets the requirements. Coming to processes, there are so many processes. There could be welding, compaction, transportation of concrete, and so on. The list is endless. Each of these processes has to meet certain requirements. Only then will the products meet the requirements, only then the components will meet the requirements, and so on. So the whole gamut of our process as far as construction industry is concerned from the point of view of quality is a very complex situation, and it's important that we understand each and every detail of whatever small bit we are looking at, and that will be the approach that we will adopt as far as this discussion is concerned in this course. Now, the thought process for quality control is closely linked to standardized methods and specifications. Test methods lay down a detailed procedure for almost all the steps involved in a test, especially for steps that are considered important from the point of view of results. We'll see this when we briefly talk about the parameters which are important from the point of view of testing the strength of concrete today, and later on in a subsequent discussion, greater details. Engineers in the field are sometimes required to interpret the provisions in a method or create a new test method itself for a unique situation, and this adaptation or modification that an engineer makes cannot be arbitrary and must be based on principles of known and relevant tests and the required performance of the produce or the process. We'll appreciate the import of these statements better when we look at some of the examples. And now the purpose of these tests could be to ascertain the performance of a product or a process and determine its acceptability, or it could be simply to compare two products or processes. Issues relating to quality control will be examined using case studies or taking up examples of simple processes from the field. And the effort will be to carry out exercises that help in understanding the issues involved and how they are addressed in a quality assurance, quality control framework. So the discussion in this course is not so much about the provisions that exist, but what considerations must prevail or may have prevailed when we introduced those provisions in a particular test method or a specification. Now, to recapitulate, major quality control methods involve standardization, inspection, sampling, testing, acceptance, and remedial measures in the event that acceptance criteria is not readily met. These are things which should be addressed in our procedures, and only then we'll be able to talk about a proper quality control, quality assurance program, and also have fewer disputes. And that's something which we'll talk about later. We'll take up and discuss some specific issues from the construction industry and look at it from the quality perspective. Some of the things that I've identified to take up as case studies is welding works, epoxy coated bars, grouts and grouting, concrete pipeline using couplers for reinforcement in reinforced concrete construction, and precast products. The last three, which are given in brackets, we will be taking up later on, or possibly I'll just upload this material on the website for you to go through on your own. The first four parts is something which we will talk about as we move along in this course. Now, we will look at this from the point of view of quality of materials, components, and systems that we talked about, and the quality of product versus the quality of a process. Now, can we look at these 7 things in the framework that is suggested in the quality of materials, component, and systems, and quality of product and quality of process framework? Now, if we look at it that way, as far as the quality of materials, components, and systems is concerned, these items fall in that category. Epoxy coated bars is a material, grouts is a material, but grouting is a process. Concrete is a material and concreting is a process. Concrete pipeline is a system. Using couplers for reinforcement in RC construction is also a material. Couplers themselves are basically a kind of material that we use at the construction site. Looking at the other side, welding is basically a process. Grouting is a process. Concreting is a process. Using couplers is a process. But precast products and the kind of considerations that go in quality control of precast products is basically a matter of quality of a product. So this is how we are going to divide our discussion. We are going to focus on bits and pieces of the construction site to better understand the issues involved in the quality control and quality assurance when it comes to a construction project site. Here's a list of factors affecting the compressive strength of concrete as determined in the compression test. There are issues relating to the specimen parameters, which could be dimensions, geometry, or moisture state. There are issues relating to the strength of component phases, which could be the matrix porosity, the water cement ratio, mineral admixtures, degree of hydration, which in itself is related to curing time, temperature, and humidity, air content, which could be entrapped or entrained. It could be aggregate porosity, which is a completely different thing. It could also be transition zone porosity, water cement ratio, and the kind of factors which is listed here. And then, of course, there are loading parameters, which could be stress type, rate of stress in application, and so on. So what I'm trying to say through this slide is that even a simple thing like the compressive strength of concrete is having so many small bits and pieces or important parameters, considerations, factors that go into determining that strength. So one of these parameters changes, everything changes. It's important to understand and appreciate this from a point of view of quality control because of the inherent possibility of any of these parameters being taken up for a very fine scrutiny if it comes to rejection of products. We'll continue our discussion today and look at another very simple issue when it comes to concrete construction. That is lapping or splicing of reinforced concrete bars when it comes to RC construction. So steel bars used in reinforcement in civil structures are generally available in lengths of about 12 meters. However, structures of height or span greater than 12 meters need reinforcement bars to be connected with each other, and this connection has to be such that the stresses, whether it's tensile or shear or whatever, carried by one bar is transferred to the next. So if we have a situation like this, that we have a bar here and we bring a bar here and we put concrete around it, and this bar is pulled out or is subjected to tension, there is no way that the whole joint or the whole member is going to behave the way it is designed to behave. So in order to ensure that, we have a mechanism for stress transfer, and one of the ways is to have a lap. So this whole joint gets buried in concrete, and whatever forces are acting on the steel are transferred from one bar to another through this lap. Now this is what is shown in the picture here, and this lap is the lap length. So there is a relationship between how much should the lap length be in terms of the diameter of the bar. Without getting into the details of that, it's important to understand that the moment there is a lap and a given cross section, there is more congestion as far as reinforcement is concerned. We are looking at, let's say, 4 bars, but here we could be looking at 8 bars, and that makes the concreting process very difficult. That's one problem. The second problem is that this lap length is actually something which is being wasted from a material point of view. This is a material which can be avoided if possible. One of the things could be, as far as economy is concerned, can we get rid of this lap length, or can we reduce this lap length, and so on. So there are different ways which have been tried as far as site is concerned. Now, why we are getting into this discussion here in this course is because of quality control issues. As far as the structure is concerned, in order that it performs satisfactorily, it has to be ensured that all these laps are proper. Basically, what it means that the stresses in this part of the bar are appropriately transferred to this part of the bar. So with that performance criteria in mind, lapping is just one of the ways of doing it. In order to ensure a proper stress transfer, checking the lap length is just one of the ways. Now let's try to see what are the implications of this kind of a splicing. Consider a typical plan of a 14-story building, which gives us an effective height of the column, let's say, of 40 meters. And if the cross section of the column is shown here, it's 600 by 600 with 10 bars of 25 diameter. We have 16 columns in this plan, and we find that we have to provide a certain lap length for each of these reinforcing bars. So if we look at a simple calculation, what we find is length of the bars is obtained from the market, let's say it's 12 meters. The lap length is taken as 50 times the diameter, which is 1.25 meters, which means that the effective length for each bar towards the height of the column is only 12 meters minus 1.25, which gives us 10.75, and the number of bars being used is 4 joints in one bar is 3. So these are the 3 joints that we'll have to, let's say, encounter on a minimum. Now the total lap length in one bar therefore becomes 3.75 meters. In a height of 40 meters, we are using 3.75 meters of lap length, which is avoidable perhaps, provided the performance is not compromised. Continuing with this simple calculation, the lap length for 10 bars in a single column is 37.5. If we take the weight per meter of a 25 mm bar to be 3.85 kgs a meter, we are wasting or using 144.38 kgs in a single column. And taking the rate of steel to be, let's say, 44 rupees a kg, the amount used in splicing per column is as much as 6,352. Now this for 16 columns is going to cost us 100,000 rupees. Now this is the kind of back of the envelope calculation which tells us that there is reason to study this issue a little bit and try to find out what are the alternatives. Now one of the alternatives is the use of couplers. Instead of using lap splicing as is shown here, we can use mechanical couplers the way that is shown here. There's no lapping, and what is done is that there is a bar here, there's a bar here, and there is a coupler which holds the 2 bars together. Without going into the details of the mechanical coupler and how they are fixed and so on, which becomes a completely different discussion, from a quality control perspective, it is important to ensure that this coupler or this joint in the reinforcing bar using couplers, the way it is shown here in all the bars, they perform in a manner that there is no compromise on the performance of the structure. There's no compromise on the performance of the steel bars. This is another view of couplers being placed at site, and we can see that once we decide to use couplers, there'll be hundreds of such couplers being used at a construction site. And that takes us to this issue of quality control. How do we ensure that the couplers being used at site are of a certain quality? How do we ensure that the bars are being properly embedded? This picture here, in fact, also tells us what will be the kind of congestion of the bars if we were not using couplers and we were using the regular splices. We must remember that the diameter of the bars plays a very important role when it comes to deciding whether or not we should use couplers or try to look into the possibility of alternatives to splicing. In a previous figure, we had seen that when doing a splice, the bar needs to be bent the way it is shown here. Now, bending this bar to this extent or in this fashion is not easy when it comes to large diameter bars. For smaller diameter bars, yes, it is possible. But for large diameter bars, it's a very difficult proposition. And therefore, the whole manual exercise or even a mechanical exercise of bending the bars to this shape adds to the cost of splicing, which we did not take when we talked about that 100,000 rupees, which is just an indicative, illustrative number. The picture also gives us a slightly different view on quality control, and that is that this procedure to ensure the couplers are good, the coupling is good, this has to be ensured right across all the thousands of bars which are used. And therefore, it's very, very important that the person who's actually engaged in that job is the person who's conscious of the responsibility on his shoulders to do a good job. Because we must remember that as far as reinforcement is concerned, it is actually going to get embedded in concrete and it will be very difficult to do anything after the concrete has been cast. And it's equally difficult to ensure that each of these reinforcing bars will be inspected before the casting is done. Of course, in certain very critical structures, it may be ensured. There may be a procedure that will take that into account. But most of the time, it would be simply impossible to do that. And that's the importance of quality control. That's the importance of educating people to do a good job. Now we move forward and try to look at another possibility, that is joining